Hacksters, what's up? I'm here with Forrest Iandola from DeepScale. What do you guys do here?
At DeepScale, we make perception systems for autonomous vehicles, mainly taking raw data from various types of sensors, using processors and neural nets to convert that into a 3D environmental model of what's going on around the car.
That's super cool. So a lot of what you do uses, for example, convolutional neural networks, which are doing object detection.
Yeah, that would be a good example of the kind of thing we do.
Cool. Other kind of stuff.
Yeah, a lot of the perception problems, 3D reconstruction would be another one. Anything you know about what's going on outside your car.
Cool. And this is mostly focused on automotive for now. Anything cool and special about DeepScale you want to share?
Yeah, good question. So a good chunk of our team actually came out of UC Berkeley, where we did a lot of research in deep neural nets, especially making them more accurate, but also squeezing them down onto smaller processors to be more efficient. And in terms of automotive, we actually started the company looking broadly at different applications, but really found a good fit in autonomous driving, driver assistance, and saving lives.
Yeah, and now you have some cool open source software tools as well, like SqueezeNet and SqueezeDet. What do those do?
Yeah, good question. So before SqueezeNet came out, which is one of the neural nets we developed, a lot of the research in deep learning had been about how do we make the most accurate models, sort of maybe unlimited computational cost. And SqueezeNet was one of the works that we did on showing how to make neural nets more practical for embedded hardware, whether that's mobile or other tiny little processors.
Right. So in terms of key emerging trends in hardware and AI and sensors and stuff, you say that there's a lot going on with sensors and processors. It seems like this squeezing might be partly to do with those processors. What types of processors are people like grabbing onto right now?
Yeah, good question. So I think a lot of the developments in hardware in general for autonomous driving are, as you say, in processors and sensors, right? So on the sensor side, it's, people talk about radar and LiDAR, but there are actually lots of different types of radars and LiDARs being developed.
Right.
And I feel it's a lot like where computer processors were in the 1960s and 70s, where it wasn't at all clear what would be the best solution, and so that's what's being figured out.
Right. On your car over there, you have a ton of different, you've got like, visible spectrum cameras, radar, LiDAR, you've got fisheye cameras, as well as like more sort of narrow ones.
Right.
And honestly, like I didn't say the thing about sensors and processors. I stole that from something that you said in an email.
That's exactly right, yeah. Oh, and on the processor side, you're asking too, as far as how's that changing, right? So what I'm seeing is a lot of companies ranging from big semiconductor companies like NVIDIA and Intel and TI and NXP, Renesas, and many of those actually license ARM technologies.
Right.
Developing more AI-oriented accelerators and processors. There are also, I think, over a dozen startups at this point developing different kinds of AI processors. I guess one interesting piece of that is a lot of that work is targeted at servers, especially for training and like web applications.
Right.
And I think sometimes mobile, automotive, and embedded are the last ones to get the latest AI technologies in terms of processors.
Because you have to do the squeezing.
You have to do the squeezing, right? You have to squeeze the hardware, and then you also have to reduce your compute footprint for the software, right? Which is one of the things that we like to do.
Wow, yeah, and you've got like a ton of different. You've got like an actual server in the car that you have over there. One thing that you've worked on in the past is, or that I believe you have, is distributing sort of training networks across different servers, which cuts down on the amount of time that you have to use. Are you using communication between cars to do that? Like, are they working together to learn, or is it all just sort of individuals?
Good question. So I guess there are a few different phases to developing and deploying a deep neural net, right? So one phase is sort of the training, right? So we take a lot of data, we develop different models, and then we train those models. And as you mentioned, to get the fastest training, we often use distributed computing. That's typically, instead of using, say, one CPU or GPU server, we'd use a whole rack of them, right? Once they're out in the car, training in the car can be a little tricky because you don't always have ground truths on, hey, if my model is confused, what's the right answer that I should learn?
Right.
So what we typically would do is to get interesting edge case, corner case data, anomalies back from the car. Tesla's known for doing this kind of thing already.
Huh.
Bring that back to our servers. Most cars have 4G radios in them at this point, or many of the new cars that are coming out have them.
Cool.
So we get the data back, and then we can analyze, how could we improve the model, retrain, and then develop better models to put in cars.
Cool.
Yeah.
You just mentioned CPUs and GPUs, but you've also mentioned DSPs. Are those digital signal processing chips?
Yeah, exactly. So a lot of the automotive chips, have all three on them.
Ah, cool. And so you think that people are using ARM chips for all three of these, or where do you think the most competitive ARM chips are?
Right. Where does ARM fit? So just to give you an example, so NXP is one of the largest automotive chip companies in the world by volume. And what companies like NXP do is they make some of their own technology, like, for example, they might make their own digital signal processor. They might license a GPU from a company like Imagination Technologies. They might license a CPU from ARM. ARM also makes GPU IP that you could use.
Cool.
And so there's kind of an ecosystem of pre-designed processors that you can pull into your chip, and then ARM is one of the most prolific companies in doing that.
Cool. And you mentioned there are also some AI-specific chips that people are developing now, which is crazy.
Right.
Is that like a hybrid between other different types of
good question.
processors?
Yeah. So I mean, there's like fuzzy lines, I would say, between GPUs, DSPs, CPUs, and other accelerators.
Because people are using GPUs for like Bitcoin mining, which is
right. They're not even graphics specific anymore, right?
Yeah, totally.
And DSPs don't have to be used for digital signal processing.
Yeah, no.
So I think one of the main architectural features that makes a really good deep neural net chip these days is being able to kind of natively support matrix and tensor operations. So rather than just taking individual numbers or vectors of numbers and doing math on them, they can do math on 2 or 3 dimensional tensors or matrices.
Cool.
So you get a lot of improvement in your efficiency and so forth by doing that.
Neat.
Yeah.
So for anyone who, like me, does not have a graduate degree in this and also doesn't have much experience, there's a really cool video series by the group 3 Blue 1 Brown that you might want to check out if you want to translate some of this stuff. It's really fascinating. We talked a little bit about challenges. So what kind of challenges are you all facing, and as an industry as well as your company?
Sure, good question. So I think at least as far as what we're focused on, there are kind of 2 use cases in cars that we care a lot about. One is the one that everybody's talking about, which is fully autonomous driving. That might be a narrow, specific streets, or it could be everywhere. The other use case is driver assistance. So that's, there are a lot of aspects to that, but you can think about that as making a car that's harder to crash, that's better at avoiding collisions, maybe helps you drive. Right. So in terms of fully autonomous driving, there are certainly technical challenges, like, can we get the right sensors, the right motion planning systems, the right maps, the right perception systems, all to work together at the right level of safety. And so there are technical challenges there. There are also regulatory challenges with full autonomy, where some countries, regions, and cities each have different perspectives on autonomy. Some require you to have a safety driver supervising the car, others don't, and so forth. So there's lots to be figured out in terms of what are autonomous cars sort of allowed to do in different places. Now on driver assistance, that's something that is basically being required by many of the governments around the world. So,
that's something I didn't know before we talked about it. That's crazy.
Yeah, it's great. I mean, to get the full star rating in some of the upcoming crash tests, it's not just about the actual crash test; it's about collision avoidance. And so I think if you've actually crashed, that's a big problem compared to if you can have intelligent software, AI-based software these days that avoids crashes.
It's cool because we're seeing a lot of work on wearables and things that interact with the driver biologically. That sounds so creepy, but I mean there are things that help help keep truck drivers from nodding off and stuff like that. And this kind of takes it to a more universal standpoint where it can, you've got the side where you're checking on the driver, making sure that they're alert and stuff, but also you don't have to rely as much on the driver. You can be like watching out for pedestrians and bikers and stuff, even if the driver doesn't care.
Yeah, exactly. So I think, I guess legal departments around the world will cringe when I say this, but I think one of the grand visions here is really to make a car, and Toyota Research Institute, Gil Pratt talks about this sometimes, or similar things like this. Make a car that almost feels like a video game with damage turned off, right? It really won't let you cause an accident in most cases.
That's really fascinating. Oh, it broke my brain for a second. So there's this spectrum between full automatic and
assisted driving.
Yeah, cool. And then there's also this balance between sort of small delivery robots style things, like we see these driving around on the sidewalks of SF all the time. They always have their little people with their
controllers. Eventually, right?
And we asked if you were more likely to see it in the small robots first before the cars, and obviously there's a regulatory component to that. But I thought what was really interesting was you said that it's more about less about the size of the vehicle itself and more about the capacity of the brain and the scope that it's expected to function within.
Yeah. So to give you some examples, right? So making a small robot or a full-size car or bigger that goes absolutely anywhere a human can, that's like level 5 autonomous driving problem, is super hard. I don't think anybody claims to have a solution for that yet, right? But if you can start to put constraints on it, that can be useful, right? So if you say, look, I have this little delivery robot that only goes on sidewalks on these particular streets and these particular weather conditions, carrying this type of payload to these kind of places, you start to have a narrow enough problem that today's technology can do a better job with it.
Right.
Now, on the size question, certainly smaller vehicles, a crash with a bowling ball size, delivery robot is maybe less hazardous than something bigger.
Depends on how fast BB-8 is going.
True. Yeah, good point.
But a car going 60 miles.
Yeah, on the other end of the spectrum, though, one of the things that's been automated, at least in some job sites for quite some time, are things like mining trucks. Trucks that are way too big to even be legally allowed on the road, that go, in and out of a quarry.
Right.
And part of why that's doable is because number one, the regulations are not so strict that it's on a public road. But number two, there's less traffic, there's less uncertainty. You can sort of predefine what the route will be. So I think a lot of successful fully driverless vehicles today, you have to think very carefully about how you constrain the case to be manageable.
Right. Is there like a hardness grading scale for? So we talked about Phoenix is easier than San Francisco. If you want to go super hard beast mode, you go to Pittsburgh because it's notoriously not so traffic. But then snow, you're playing around with snow in Tahoe because that's a challenge as well.
We are.
Disrupts your beams and throws them everywhere and stuff. I don't know, has anyone come up with sort of a scale?
Yeah, that's a good question. I feel like our industry is just finally settled on having 5 or 6 levels, like from level 0 to 5 of autonomous driving or driver assistance. But I think once you cross from level 3, which is a pretty advanced driver assistance system, to level 4, which in a constrained environment may not ever need human intervention.
Right.
And the no human intervention thing, I think the next thing that we need to work on collectively is trying to figure out what are the easier and harder cases. And when a hard case pops up by surprise, how do we deal with that, right? Do we do some sort of escape route planning where we say, at any given time, we have a few good plans for how to just get off the road because it's gotten too crazy.
Right.
But no, I don't feel like that standard exists yet, unfortunately.
So it goes, I guess, they're so varied and the terrain is so depending on the size of the area you're going through and the roughness of the terrain and the weather and the people and the traffic and everything. It's so many
there's so many complexities.
It seems like it wouldn't be feasible to not develop such a thing right now.
Yeah, I mean, you would enumerating every hard case would take a long time, right? I mean, because the number of cases you could potentially encounter are infinite, right? I mean, it's like the number of permutations of atoms in the universe or something, right?
Yeah.
So it's hard to write them all down for sure.
So that's what's cool about the convolutional neural network stuff you're doing, because I read that it is made so that you require the least amount of pre-processing, so that you can basically be dropped anywhere and you'll do pretty okay, as opposed to, if you get a bunch of like pre-processed data, then you can like be an expert at it. But like, once you hit a case you're not familiar with, I don't know. So
I think that's about right. Yeah.
Yeah. Oh.
Do you want me to talk about that, or or you have a question?
Sorry, I do have a question.
Okay.
Sorry, I got really excited about all this Googling I did. Okay, so in regards to your research, though, you've done work on, for example, recognizing the biological effects of meth. You've done research on focusing electron beams for linear accelerators.
Mm-hmm.
What are the most interesting problems that you're facing right now? Do you get to play with those as the CEO, or?
Good question. So as a company, I think some of the most interesting problems are, how do we actually analyze how well our system's working, right? So there aren't actually a lot of standard metrics that map to the real driving problems. So for example, if you look at, on the driver assistance side, there are safety tests run by IIHS and Euro NCAP and NHTSA and other regulatory bodies. They often have a pretty clearly defined testing criteria.
Yeah.
Right, where you could maybe almost memorize some of those tests.
Right.
Where what we really want is to test really hard cases that you might never think of. And so I think one of the interesting challenges here is how do we internally, as well as how do we help the community figure out what's a more comprehensive way of testing not just the code coverage and software quality, but the ability to handle harder and harder cases.
Yeah, that's super meta, because you have to test for things that you haven't thought of yet, and that's the point of it. Oh wow. Yeah. Okay.
I think one theory about that is there will be some mix of simulation-based testing and real-world testing, where you can maybe cover more bases that way.
I wonder if there will be soon well, have you ever thought of participating in the DARPA challenge with the robot vehicles in the desert and stuff?
Yeah, I guess that ship has mostly sailed. That a lot of those challenges were in sort of 2005 to 2010 range.
Oh, my information is old.
No, it's fine. Yeah, but I think we have had sort of a phase where it's gone from, I think the DARPA challenge really helped to get this technology off the ground, especially on the building a complete vehicle that does at least some autonomous things, right? And now we're sort of at the commercial sort of scaling side of it, right? Of how do we is a community build product around this.
Cool. So we also asked, how soon before we see pizza drones? I don't know. Is there a food that you think would be better than pizza? What's the optimal food for drone delivery?
I don't know. I somehow biryani landing, in my front yard from a drone sounds pretty great.
That'd be amazing. How long till we get biryani drones?
I think it's probably been done.
Yeah.
Yeah. I mean, I've definitely seen prototype food delivery drones, and I think the more widely discussed ones, for example, were more on the driving side, like Ford and Domino's did the pilot of pizza delivery cars.
Yeah.
So I think a lot of this stuff, again, if you constrain some of the environment and so forth, is reasonably feasible today. I think some of the questions around that are more, at what point can these systems do a broad enough range of locations and stuff to really make a dent? And also, I mean, what's the hardware and operations cost of the system versus labor, right, to have humans do it?
Yeah, right.
So I guess my sort of cop-out answer is I'm not sure. It's always hard to predict exactly how quickly scalable rollouts will come, right?
Yeah.
I almost think of it when smartphones started to come out, nobody really predicted what the apps would be, right? And so I think similarly, the broader range of things we can do with driving, as well as just having more sensors and computation in cars, opens up a lot of things where it's hard to guess what all low-hanging fruit cases will be.
Yeah, and which bits of it people will embrace, because I feel like there's a cultural part of that as well.
Yeah.
You never know. Yeah, with Google Glass, they introduced that, and they think it's going to be this great assistive technology, but it just looks terrible and people hate it.
Right.
People, if you have any questions for Forrest, jump in. Feel free. We've got the excellent Katie from Hackster is hanging out in the chat to see if you've got questions. So we're happy to address those. In the meantime, so, going forward, you've mentioned that, the DARPA stuff is in the past, but you have had a couple of hackathons around your office or with your technology, and you're maybe planning on some more of those?
Yeah, still figuring out the exact plans, but yeah, I think hackathons are a great way to try new things in a low pressure environment, right?
Cool.
So, and I think both externally, we've been involved in some university hackathons and so forth. We plan to do more of that, and internally, we definitely, I think in terms of our culture, really encourage, creativity.
Cool.
One fun thing about solving a very specific set of problems in perception is we get to, not be total workaholics. It's like a fairly specific problem, but then think very creatively about it and spend some quality time every day working on it.
That's super cool. You guys have all kinds of stuff on GitHub.
Yeah.
You have a whole open source page. Are you looking for people to contribute to that stuff?
Yeah, so one interesting set of contributions we've seen pop up is when we released SqueezeNet. I think within about 2 or 3 days, we were back in the day, Caffe was one of the more popular neural net frameworks. Now there's Caffe 2 and TensorFlow and MX.
Caffe with 2 Fs.
Yeah, CAFFE. Yeah. Anyway, so there's kind of a handful of popular frameworks or software tools for implementing neural nets. And within a couple of days of releasing SqueezeNet, people had found it and forwarded it to a couple of their frameworks, and now it's in most of them. Actually, even ships by default in some of the frameworks.
And you have some that you can't share yet, but you've still shared the papers because you think that's going to help push the culture forward. Yeah,
definitely. I mean, I think we're at a stage, especially with some of the problems where getting the research community involved is what we need to be able to make progress.
Awesome. Cool. So anyone out there who is interested in researching this stuff, get involved with one of the hackathons, check out the GitHub page. Any other ways people should interface with you?
Twitter, LinkedIn. Yeah.
Awesome. Get in touch. Thank you so much, Forrest, for chatting with us. We'll be in touch if people have any other questions. We'll be sure to forward those on to you and hope that we don't take up too much of your time. But sweet. Thanks for being an Arm Innovator.
Yeah, thanks a lot. I enjoyed it.
Cheers. Thanks for watching.